Hi, I'm Carlton Coffrin. In this video, I'm going to share with you some of the debugging strategies that I've developed for working with the D-Wave quantum computer at Los Alamos National Laboratory. Before we jump in, it's important to note that this video assumes you have a basic understanding of the D-Wave quantum computer and the tools that are provided with it. My basic approach to developing debugging strategies is to handcraft very small examples. The reason for this is that you want to know the correct answer for the example of interest. So in the case of doing optimization, you want to be able to compute the global minimum of your problem so you can see how it compares to what's coming out of the hardware. If you're interested in a sampling type of application, you want to be able to enumerate all the states and compute the partition function for the distribution that you're trying to sample from so that you know how closely the computer's output matches the sampling that you're trying to generate. What I'll share with you in this talk are some examples from my experience. This is by no means a comprehensive talk on how to debug on the machine. Here's an example of one of the first very simple type of test cases that I developed to test my understanding of the machine. I call this the all-negative example because I set all of the couplers in the machine and the local field of every spin to -1. And this is an example for the Ising chip at Los Alamos that uses the top left corner of the particular chip. If you're interested, you can try and cut and paste the textual representation from the left-hand side into the QBIS system and run this test for yourself. Now, the cool thing about this particular input is that it has nice known properties. It has a unique global optimum where all the spins are set to 1, and you can easily calculate the minimum energy value. In this case, it's 19. So when I say you want to build small examples, this is a good illustration of that. Here's an image of the software stack for the D-Wave quantum computing, and there's a lot of different tools here. I would break them up into these different levels. So basically, if you're working at one of these higher levels, if you need to debug this particular level, you need to move down to one lower level of detail. So if you're working with 2Q or QSage, then to debug it, you need to start trying to implement your model on QBsolve. Now, assuming that you're working with QBsolve, then to debug your model, you need to go down one layer lower and then start trying to implement your problem on the SAPI interface. And then last but not least, if you're working in the SAPI interface and you're trying to debug the output of the machine, you need to then start reasoning over these quantum machine instructions, which is the actual data that you're sending to the chip and what it's returning to you. Now, it's important to note that no matter what level you're working at in the machine, you can always jump to this quantum machine instruction level to inspect what you're sending to the hardware. So if you log into the SAPI interface and you review the problems you've submitted, you'll see some of the most recent things that you've submitted, and you can click on them, and you can view exactly what was sent to the hardware. So this can be really useful just for trying to understand what kind of instructions are being generated for a particular tool that you're using. Now, I believe there's a pretty big difference between how you do debugging above, including QBsolve and above, or how you do debugging in the tools that are more at the SAPI level or the quantum machine instruction level. My particular experience has really focused on the quantum machine instruction, so this tutorial will be biased to this particular type of debugging. Now, why has my work focused on that particular point? Well, what I have observed is that many quantum computation workflows have this particular form. You have your problem of interest, you're going to apply some transformation to that problem, you're going to send it to the quantum processing unit, then you're going to get some solutions back, you're going to perform an inverse transformation on those solutions, and then you have answers to your particular problem. So the issue is that if the quantum processing unit is like a black box, and we don't have a good intuition for what it does, it becomes very hard to debug the transformation which is putting the problem into the machine. So essentially, you just start playing with the transformation at random, and that's not a very efficient way to debug your code. So this brings us to a very interesting question. What do you expect the quantum processing unit to do for you? You might take a minute, pause the video, and think about what is your expectation of what the machine will do for you. Now, I would argue this is a bit of a trick question because I don't think anyone knows exactly what the quantum processing unit does. But I'll take you through my experience trying to learn about what it might do and what my experience was. So when I was first trying to answer this question, I read that the machine is an adiabatic quantum computer. So I went and I read this very interesting Wikipedia article. I watched a number of really fun videos on D-Wave's website. I learned about things like eigenspectrum and energy levels and lots of different things like that. What I concluded from learning all about adiabatic quantum computations is that this model is all about global optimality and ground states. The basic theorem is that if you anneal slowly enough, so the processing time goes slowly enough, you will always stay in the ground state and you will have the best answer. So let's try to build on that intuition and test this using the real hardware. Here is an example of what I would call a Chimera Degree 2 RAND4 instance. We're currently developing a tool called Dewig, which helps you generate problems like this to build your intuition and test the hardware. So what we're going to do here is just submit this particular problem and request from the hardware to generate 1,000 samples at 20 microseconds. This is the distribution of solutions that come out of the hardware when I ran this for this tutorial. And what I'm going to do is collapse all the solutions that have the same energy value and sum them up. And then, so instead of having a distribution for all the different states, we just have a distribution over energy levels. Now, it's important to note that if you download the slides for this tutorial, it includes all the data for these particular inputs, so you can try repeating these experiments on your own time if that interests you. So now the question becomes, does this look like the optimal solution? And given that over 90% of the samples all returned a value of an energy of minus 35, I would say yes, it looks very much like the optimal solution. This matches our model for what an adiabatic computation does. So let's try something a little bit different. Let's make the problem a little bit bigger and study a 3x3, which I would call Chimera Degree 3 RAND4 instance. Here, if I submit for 1,000 samples at 20 microseconds, I have a distribution like this, and you can see that there's a bit of a hump. The mass of all of the solutions is around minus 72.75, and there are a few that are minus 73.25. Now, you have to keep in mind that the D-Wave is an analog machine, so these kind of little differences can be due to a lot of different factors, including some kind of small errors while writing the test case, or noise. So I would be inclined to say that this small difference could be a numerical issue that's really causing us to see that some solutions look better. Only a few solutions look better than the other ones. So just for the sake of argument, let's try rounding some of the coefficients in this problem, and again, take 1,000 samples at 20 microseconds. Now, this is the particular distribution I get when I do that. Now, there are two interesting observations. The first one is there's a lot of different states that are better than the mass, which is around 74.5. And most importantly, there are about 11 that are about a full unit less than 74.5. So this is looking less like a numerical issue and more of like an annealing type of an issue. So let's apply our understanding of the adiabatic theorem and increase the anneal time. We would expect by doing this that we're going to get more solutions from the lower energy state because we're annealing at the right speed. So due to some hardware requirements, we have to reduce the number of samples we're taking to 500, but we're going to increase the anneal time from 20 microseconds to 2,000 microseconds. So this is 2 orders of magnitude increase in how slowly we anneal, we perform the annealing step. This is the particular set of solutions that came out of the machine when I did this, and the interesting thing we can ask ourselves is, what changed about the distribution of the solutions? And it's not that much. You can see we still have a significant mass around 74.5, and then there's a few solutions at 75.3. So we can return back to this question. What do you expect from the quantum processing unit? It seems like that adiabatic story was not working out for us based on that little experiment. So my recommendation would be to not pay attention to this particular theorem, and let's build a different intuition for what the machine does. What I've learned in my experience trying to debug things on this machine is that it doesn't behave like an optimization tool striving for global optimality or ground state. It behaves much more like a sampler from a Boltzmann or Gibbs-like distribution. So if we assume our states are -1 or 1 sigma, and we have the couplings J in the field H, the Boltzmann distribution would be defined by this particular equation. Now, you can observe that we know pretty much all of the information in this equation except for beta. And it turns out that you can actually use some kind of machine learning techniques to estimate what beta is, and it lies somewhere around 6 for some test cases that were recently done. So this is actually very interesting and good news, because sampling from a Boltzmann-like distribution is kind of like doing probabilistic optimization. So maybe it's both a sampler and an optimizer at the same time. But in any case, let's test our intuition for if this thing behaves like a sampler from a Boltzmann distribution. Here's a particular pattern which I like a lot for testing because it has this kind of beautiful checkerboard look, and there are two unique optimal solutions to this particular problem. Basically, all the columns and all the rows of these Ising bits take the same spin, and in this particular size, which is 3 by 3, the minimum energy is 176. So we have a good understanding of what we expect to get out of this particular Ising model. So what we're going to do as an experiment is we're going to try weakening these couplings between all of the different spins in our problem, and this will have the effect of simulating the Boltzmann distribution temperature increase, because as we weaken the couplings, the effective temperature of the distribution is increasing. Now, it's important to note that if you're going to try to reproduce this experiment on your own, it's important that you turn off the auto-scaling property, because otherwise the machine will automatically rescale the problem and you won't see this simulated increase in temperature. So let's begin with step 1 with a coupler scale of 1.0 and put this particular problem into the machine for 1,000 samples at 20 microseconds. What we see is we only have two particular states, and they both have what we know is the minimum energy value of minus 176. Now, if it was a perfect Boltzmann sampler, these would be 50-50. So already we can see that there's something a little bit off, but anyway, let's continue with our experiment. We reduce the coupler scaling by half, which has this effect of increasing the temperature of the distribution. You can see that the energy values have gone from 170 to 88. They've been halved. But once again, we still get the two lowest energy solutions, so this is looking pretty good. Let's divide it by half again. We still get this, the two lowest energy solutions with all of the samples. Now, once we get to a scale of 0.125, now we start to see that we get primarily the two ground states, but there's a few other solutions there where essentially they're getting bumped out of the ground state. So some kind of like high temperature effect is causing you not to get to the bottom state every time. What happens if you increase it again for a coupler scalar of 0.625? Now you can see that a more significant portion of the samples have gone above the optimal solution, the ground state. And then if you decrease it once more, now we're at a point where basically we have almost pure randomness, and then almost none of the states are taking the lowest energy that they can possibly be. So this seems to suggest that our intuition for a Boltzmann-like sampler is correct, and it's my experience that it matches the behavior of the machine better than thinking about the adiabatic model. Now, before we conclude, we're going to switch topics to another interesting and challenging problem with debugging quantum computations, and that has to do with tools that are these properties which are called chains. So before we can explain what chains are, we have to talk a little bit about the properties of the chimera graph, which is the graph that the D-Wave quantum hardware implements. The first thing to observe is that the D-Wave chimera graph is a bipartite graph. And the consequence of this is that there are no odd length cycles. So you can try playing around in the graph by bouncing from two particular nodes to another, to a third node, and then seeing if you can draw an edge back. And you'll always see that there's no way that you can make that third edge come back to the starting point. You can even try jumping between different cells, and you'll still have this same problem. The second property to notice about the chimera graph is that the maximum degree of any node in this chimera graph is 6. So if you look, it doesn't matter if you're at the top of one of these stars, you always connect to 4 people in your local cell and 2 people at your neighboring cell. Whether it's left or right or up and down, it always has that property. So now we're in a position to talk about what chains are. The chains can arise in 2 particular cases. It depends on what logical problem you want to implement. The first case is that you have a logical problem with an odd length cycle, and the second case is that you have a logical problem where you want one particular spin to interact with more than 6 other spins. So that's the case 2. So these are the logical problems you want to solve. What is the physical implementation of this on the D-Wave hardware? The typical approach is to create a second spin, like sigma 1 prime, which is basically a duplicate of the sigma 1 spin, and then link them together with a very strong negative coupling so that they take the same value. Effectively, if that coupling is strong enough, it'll effectively implement what is going on in case 1. In case 2, it's the same idea. You make a new duplicate of the spin variable, and then you connect them with a strong negative coupling, and then you're able to basically get 8 edges connecting a particular spin. So these special edges, which are basically linking these replicated variables, sigma prime 1, are called chains. So let's explore what it's like to use chains in what's called a frustrated odd cycle. So the reason this is called frustrated is there's no way to make all the spins happy. In this particular example, you can see that spin 2 and spin 3 want to take the same value, spin 1 and spin 2 want to take the same value, but spin 1 and spin 3 don't want to take the same value. So there's no way to satisfy all 3 of these couplings at the same time. In this particular problem, there are 2 minimum energy solutions. The first one is this, where all of the spins take the value of 1, and the second one is this, where the 2 blue ones take the value 1, and the gray one takes the value -1. So let's look at how we would implement this particular problem on the D-Wave hardware. We would introduce a new spin, sigma 1 prime, and link it together with the strong negative coupling. Now, this has a low energy solution here. It also has another ground state here, and then it has a third ground state, which the original problem did not have, where these 2 gray dots take different values. So what's going on with this new ground state that was introduced by our implementation problem? Essentially, there's a broken chain here. So you can see the 2 gray circles take a different spin value than before. So there was no way to represent this particular solution in our original logical problem. Now, before I tell you how to resolve this issue, let's just double check it on the hardware to see how this works. So you can see in this particular graph, it's essentially the exact same image I've shown you, rotated by 45 degrees and squashed. So it's the exact same thing we've been talking about. If you run this in the hardware for 1,000 samples at 20 microseconds, you get a distribution that looks like this. And you can see that these 3 ground state solutions occur in this particular proportion. Now, an interesting thing to observe is that the hardware is basically chain blind. It has no idea that you don't like this solution because it violates your logical problem. To the hardware, it's just another ground state. Now, you might ask yourself, well, what's the big issue? These are all ground states. They all have the same energy. Maybe they're all fine for me. Well, the problem arises when you try to project a solution from your implementation back to your logical graph. So if you're trying to say, okay, I've got this solution where the gray takes 1 and -1, when you map it back to your original problem space, what spin should you give sigma 1? And I don't think there's any particularly good answer to this. There's a lot of heuristics for different approaches for how to do that. But this is essentially the challenge of broken chains. When the chains break, it's not obvious how to resolve those ambiguities. So here's one particular solution to solving this problem. It's not the only one, but probably the most straightforward one. The idea is to increase the chain strength to eliminate incorrect ground states. So essentially what we're going to do is we're going to keep that chain at the strongest value can be, -1, and we're going to make everything else in the problem a little bit weaker to compensate, to give it a stronger weight. Now you can see when we do that, now we have two particular ground states which take the value -3.5, and we've eliminated that bad ground state we didn't like. So let's try running this particular implementation in the hardware, and we'll run 1,000 samples at 20 microseconds. And indeed, we only get the two ground states. So compared to the configurations we had before, we're getting the two logical problems we wanted, and we've essentially solved our broken chain problem. So that's the basic overview of chains and why they are a little bit tricky to deal with. Now here's some food for thought that you can go and think about after the tutorial. What are the implications of increasing the chain strength if you have a Boltzmann-like sampler? And another question is, what are the implications of longer chains if you have a Boltzmann-like sampler? We'll leave both of these questions for another lecture. So just to close on debugging on the D-Wave machine, the debugging on D-Wave is extremely difficult, so I highly recommend you focus on super small test cases where you have a very good understanding of how you expect them to behave. In the D-Wave documentation, there's a lot of talk about optimization, but this does not match my experience with how the machine behaves. I found it's much better to think of the machine as a sampler and then integrate it into tools as kind of a sampling tool. Once again, take care with chains, because setting this chain strength parameter can be very challenging and can have very interesting side effects. And last but not least, it's very important to test your algorithms on the actual D-Wave hardware as much as possible. I would argue that no one fully understands what the machine is doing, so no one knows how to emulate it. So testing on the hardware is very important. Otherwise, you could experience very different results when you switch from a simulator to the hardware implementation. Well, that's the end of this debugging tutorial. Good luck, and we hope you enjoy the quantum computations.